Hi, this is Mrs. Boland with the University of West Florida, lecturing for Mod 6 for Elements of Statistics, STA 2023. We're in the fall 2018. This will be an unedited copy of my teaching, so hopefully we won't have very many mistakes, but you might hear my family in the background or dogs or something of that nature. I apologize for that, but we're doing the best we can. Okay, let's get started. The first thing we're going to talk about is the graphs of the normal probability distribution. We're going to be talking about the normal probability distribution. That's what Mod 6 is about. We've been discussing in Mod 5 discrete probabilities, which are countable. Well, we're going to be learning how to determine the probability of events and occurrences when the data is continuous. So that's why we're going to be switching over to the normal probability distribution, because that deals with continuous data. So we've learned how to deal with discrete data. Now we're going to learn how to calculate the probabilities when we're dealing with continuous data. So when we look at a relative frequency histograms that are symmetrical and bell-shaped, these are said to have a shape of a normal curve. Okay, we have a shape of a normal curve. So we have a frequency histogram that is symmetrical and bell-shaped. They're going to have what's called a normal curve. For instance, consider the histogram pictured below. Let me scroll up just a little bit so you can see those clearly, which represent the IQ scores of 10,000 randomly selected adults. Note that as the class width of the histogram decreases, the histogram becomes closely approximated to the smooth red curve that is pictured along the histogram. So you can see each of these have a red curve. Do you see that? Okay, and that's what we're talking about when we're talking about the red curve. You can see it on each of these right through here. For this reason, the normal curve can be used to model the distribution of continuous random variables. In mathematics, a model is an equation, a table, or a graph used to describe reality. Okay, so we have tools: an equation, a table, or a graph that we use to describe or model, okay, what's really happening in real life. The red curve in the figure below is a model called the normal curve, which is used to describe continuous random variables that are normally distributed. Okay, so what you want to notice is that we have a symmetrical curve. Symmetrical meaning what you have on one side, you have on the other side. Okay, and everybody's heard of the bell-shaped curve. It looks like a bell, and that's what we're saying. Okay, that is those are two of the several properties of a normal distribution that are important to identify. Take a moment and let's look at these. Are these a normal curve or not? Okay, so study the three histograms pictured below and determine if a normal curve can be used to model the continuous random variable or not. Okay, so I'm going to let you take a moment. Okay, the first one, it says it's the birth weights of babies whose term was at 36 weeks. In other words, they were born 4 weeks early at 36 weeks gestation. If you look at this one, is it a perfect normal distribution? No, it's not. But it's close enough that I would think that you could go ahead and you could say that we could get a normal curve out of that, okay? Is it a perfectly normal distribution? No, but it's very good and very close. This one here is skewed. Absolutely not normal. This one here, if you look at it, you can see again that we can go ahead and we can approximate. This is a very good example of normal distribution. This is the Rhode Island red hens incubation times. Okay, so they've got that down to a very good process right there with incubating out the Rhode Island red hens so that they do follow a normal distribution. Let's go ahead and review the properties of a normal curve or the normal distribution. Important properties of the normal curve. Number one, the curve is bell-shaped with the highest point over the mean. Okay, so it's bell-shaped, looks like a bell. The highest point, the peak, or the center, is where the mean is, okay? Number 2, the curve is symmetrical about the vertical line going through mu, okay? Symmetrical. What happens on one side is a mirror image of what happens on the other side, okay? Number 3, the curve approaches the horizontal axis but never touches it. You see right here, visually it looks like it touches, but the reality is it never touches or crosses it, okay? It's okay to draw it where it does physically touch, but just you need to know that it gets infinitely close, but it never actually approaches this horizontal axis. Step number 4, the inflection or transition points between cupping upward and downward occur at mu plus 1 standard deviation and mu minus 1 standard deviation. So here's mu minus 1 standard deviation. Here's mu plus 1 standard deviation, and you draw your points up at the intersection. Right here and right here are the inflection points. So up until from mu out to negative 1 standard deviation to plus 1 standard deviation, we have a downward cup. You see that? It opens downward. But at this point, we switch and it goes upward. Okay? So that's what that means. And then the area under the curve under the entire curve is equal to 1. So the area under this curve right here, okay, is equal to 1. And when I say area, that's exactly what I mean. So if I had a bedroom that was 10 feet long by 8 feet, and I wanted to know what the area equaled, it would be equal to 10 times 8, which would be 80 feet, right? This would be the area in this rectangle. Well, here, the area underneath this curve, the shaded area, equals the value of 1.0, okay? 1.0. Okay, one of the rules that you need to learn is called the empirical rule. The empirical rule says that for a distribution that is symmetrical and bell-shaped, in particular, for the normal distribution, we can say that approximately 68% of the data values will lie within 1 standard deviation of each side of the mean. Approximately 95% of the data values will lie within 2 standard deviations of each side of the mean. Approximately 99.7% of the data values will lie within 3 standard deviations of the mean. So what does that mean? That means that we have a curve, it's bell-shaped, it's symmetrical, okay? Those are the two part that it has to be symmetrical and bell-shaped. When we have any distribution that is bell-shaped and symmetrical, half over here, mirror images of each other, then we know that approximately 68% of the data values lie within 1 standard deviation of the mean. So we know that the mean is in the center, and if we calculated the standard deviation for the data set at hand, we could add 1 standard deviation to the mean, and we would find that this area right in here, that 30% of the data values lie between the mean and plus 1 standard deviation. We can also say that we know that 34% of the data values lie between the mean and minus 1 standard deviation. Okay, they would fall between here. If we look between negative 1 standard deviation and plus 1 standard deviation, that would be that lie within 1 standard deviation of each side of the mean. So that would be plus 1 standard deviation, minus 1 standard deviation, that the area under the curve in here is going to be 68%, and that 68% of the data's values will lie between this value and this value, okay? We know that 95% of the data values lie within 2 standard deviations of the mean. So if I go mu plus 2 standard deviations, it's going to take me out to here. So instead of having just 34% of the data between mu and plus 1 standard deviation, we're going to add a little bit more on, and we end up with 0.475. So we'd have 0.475, which is the 34% plus the 13.5% of the data values fall between mu and mu plus 2 standard deviations. Okay, so 47.5% of the data values fall between mu and mu minus 2 standard deviations, right in here. Or we can say that 95% of the data values fall within 2 standard deviations of the mean. So within 2 standard deviations of the mean, 95% of the values fall. If we look at 3 standard deviations, okay, from here to here, we have 99.7% of the values fall between -3 and +3 standard deviations of the mean. Okay? Okay, let's look at the properties of the normal curve. When we look at this, it says here's 2 different continuous random variables that are modeled with the normal curves pictured below. The model of the variable x is on the left, and the model of the variable y is on the right. Use the models to answer the questions that follow. So question A, identify the mean and standard deviation of x. So here's x, okay? We know that our mean is found in the very center, right? So we know that the mean of x is going to be equal to 100. And it says find the standard deviation. Well, we're going to know that this is 1 standard deviation away, 2 standard deviations away, 3 standard deviations away. So to find the standard deviation, all I need to say is what is 115 minus 100, and that is equal to 15. So the standard deviation of x is equal to 15. Now let's look at our next question here. Okay, part B says identify the mean and the standard deviation of y. So here's our y distribution, and in the very center is going to be our mean. So our mean of y is going to be equal to 530. Our standard deviation is going to be calculated, of y is going to be calculated at, here's our standard deviation plus 1, so it's going to be 630 minus 530, and so that is equal to 100, okay? So here we have 2 different distributions. They're both symmetrical, normal distribution, but we have a mean on x of 100 and the mean of y of 530. The standard deviation for x is 15. The standard deviation for y is 100. So that tells us that the data in x is much closer clustered together, clustered closer to the actual mean than over here on y, because the data is more dispersed. Okay, question C I just looked at says which variable has more dispersion and why, which we just answered. Question D says using the model for a random variable x, that would be this one over here, what percentage of occurrences would we expect to find between the value of 85 and 130? Okay, so question D is what percentage of occurrences would we expect to find between 85 and 130? So 85 right here, let me highlight the area of interest, 85 and 130, okay? This is the area that we're interested in. Now if you look, you're going to notice that the area from 85 to 100, right in here, this is just 1 standard deviation away, correct? So for part D, we're going to have 34% of the data right in here, correct? So it's going to be 34% of the data between 85 and 100, and then plus from 100 to 130, that right in here is going to be the 47.5. So plus 47.5%. So we simply add those 2 numbers together and we get 47.5 plus 34 is going to be 81.5. Oops, 81.5 of the data is what we would expect to find between the values of 85 and 130. Okay, all based off of the empirical rule. And then part E says, what percentage of time would we expect to see the occurrence of Y that is greater than 630? Okay, let me see if I can copy and paste that in. Okay, here we go again. So, I was able to copy question D in and question E. Okay, so I put the picture in so we can see it a little bit easier here. What percent of the time would we expect to see an occurrence of Y that is greater than 630? So that says greater than 630. So that's going to be all of this area under the curve. Okay, do you agree? Greater than 630. So the probability that Y will be greater than 630. Now, I know that the area under the whole curve is equal to what? 1.0. I know that it is symmetrical about the mean, which means 50% of the data is to the left or negative of the mean, and 50% of the data is to the right of the mean. So knowing that 50% of the data is to the right of the mean, I have 50% to the right of the mean, okay? And I know that from the mean to one standard deviation, the mean to one standard deviation, right in here, this green part, right in here, I can color this in sufficiently. Okay, this green part is how much of the data? It is 34%, right? Because from the mean to one standard deviation is 34% of the data. The mean plus and minus one standard deviation is 68%, but I'm only looking at this half, so that's 34%. So what is 50 minus 34? That is 16% of the data is going to be greater than 630, okay? Because I know that 50% of the data is in this whole curve. I'm looking for the blue area here. I know the area here in the green, so if I know the whole portion is equal to 50%, I subtract off the 34% in the green. That gives me my balance of what the blue is, which is 16%. Okay, the yearly wheat yield per acre of a particular farm is normally distributed with a mean of 35 bushels and a standard deviation of 8 bushels. Okay, we're talking wheat. We know it's normally distributed. We know that the mean is 35 and the standard deviation is 8 bushels. It says label the 68, the 95, the 99.7 pieces of the distribution. So let's go ahead and draw our standard normal curve. Okay, so there's my curve. We're going to put the mean in the very center. And the mean is 35. And it says label the 68, 95, and 97% pieces of the distribution. So if I start off and I say I want to do the mean plus one standard deviation, that would be the mean plus one standard deviation is going to equal to 35, that's my mean, plus 1 times my standard deviation, which is 8, and that is going to be equal to 43. So we can say mu is equal to 35, and we can say our standard deviation is equal to 8, and so our first number right here is 43. Okay, now let's do minus 1 standard deviation. So we come over here and we say mu minus 1 standard deviation is going to be equal to 35 minus 1 times 8, which is equal to 27. So right here is 27. Now we're going to look at 2 standard deviations. So if I go mu plus 2 standard deviations, mu is 35 plus 2 times my standard deviation. That's going to be 35 plus 16, and that's going to equal to 51. So we have 51. Now we're going to go mu minus 2 standard deviations. So that's 35 minus 2 times 8, which is subtract 16, and we're going to get 19. So 19. So what we're saying here is that our average production on any field is 35, okay, for this one particular farmer, okay, per acre. They yield 35 bushels of wheat per acre. 68% of the acres will yield between 27 and 43 bushels of wheat. 95% of the acres will yield between 19 and 51 bushels of wheat per acre. Now let's do our 99.7. So if I go mu minus 3 standard deviations, that's going to be 35 minus 3 times 8, which will be 24, and that is 11. So 11, and then we go mu plus 3 standard deviations. That's going to be 35 plus 3 times 8, so that's going to be 35 plus 24, and that's equal to 59. So 99.7% of the fields or the acres of this particular farmer will yield between 11 to 59 bushels of wheat per acre. Okay, so that's our label of our distribution. Question B says, what percentage of the distribution is covered by 19 to 35? So 19 to 35, that would be this part over here. 19 to 35, this part right in here. And what area under the curve is that? Well, this goes to 2 standard deviations, right? So if we take 95 and we divide it by 2, we know that the percentage, because it's asking for it to be percentage, would be 47.5% is covered by the 19 to 35 bushels yield per acre. Okay, so 47.5% of the farmer's fields would yield between 19 to 35 bushels of wheat per acre. Okay, now part C, it says, what is the probability that the yield will be between 19 and 35 bushels of acres? Well, that's the same as part B. So we are going to refer to the green shaded area, and we have 47.5% of the curve shaded. That was answer to part B, and that corresponds to the probability then of 0.475. Okay, so we would just take the percentage and convert it into mathematical notation, and that gives us our probability then of 0.475. Okay, area under the normal curve. Suppose that a random variable x is normally distributed with a mean mu and the standard deviation sigma. The area under the normal curve for any interval of values of the random variable x represents either A, The proportion of the population with the characteristics described by the interval of values, or option B, the probability that the randomly selected individual from the population will have the characteristics described by the interval of values. Let's explain what that means a little bit more in detail. For instance, the weights of giraffes are approximately normally distributed with a mean of 2,200 pounds. Oops, I thought I was in highlighter mode. Let me go grab a highlighter. Okay, so 2,200 pounds. The standard deviation is 200 pounds. The normal curve with the parameters labeled follows. This area to the left of 2,100 pounds is shaded, okay? So here's our mean, right here in the very center. Here's our normal curve. Here's, let's see here, we're at 200 pounds for standard deviation. So there's actually from here to here is 1 standard deviation. Here to here is 2 standard deviations. And here to here is 3 standard deviations. You gotta look at your label. So starting at the mean, from here to here is 1 standard deviation. From here to here is 2 standard deviations. And from here to here is 3 standard deviations. So the shaded area actually starts at a half a standard deviation away from the mean, okay? Because the difference between 2,200 and 2,100 is only 100 pounds. Our standard deviation is 200 pounds, so 100 is half of 200 pounds. Now, if the area under the normal curve to the left of x equals 2,100 pounds is equal to 0.3085. So what we're saying is if the area under the curve right here is 0.3085, this area right in here, that should be a 0, there we go. This implies that the proportion of giraffes whose weight is less than 2,100 pounds is 0.3085, okay? So the proportion of giraffes whose weight is less than 2,100 pounds is 0.3085, or almost 0.31, okay, less than 2,100 pounds. And the probability that randomly selecting a giraffe that weighs less than 2,100 pounds is equal to 0.3085, okay? So the probability of randomly selecting one giraffe who weighs less than 2,100 pounds is 0.3085, or approximately 0.31. Okay, the GRE is a test required for admissions to many U.S. graduate schools. Student scores on the quantitative portion of the GRE follows a normal distribution with a mean of 150 and the standard deviation of 8.8. In addition to other qualifications, a score of at least 152 is required for admissions to a particular graduate school. Draw a normal curve with the parameters labeled. Shade the region under the normal curve that represents the test takers who score above 152 on the quantitative portion of the GRE. So let's just go ahead and start. Let's grab some ink and we'll draw our curve. And we're going to go ahead and label our mean in the center. And remember, our mean is 150. Okay, and if we wanted to add on our parameter of standard deviation, it would be 158.8 would be plus 1 standard deviation, right? Oops. And then the standard deviation subtracted off of 150 would be 141.2. So I just put on plus 1 standard deviation minus 1 standard deviation. I didn't do 2 or 3 standard deviations. Now it says shade the region under the normal curve that represents test takers who scored above 152 on the quantitative portion of the GRE. So we're going to put 152 right about here, 152, and we're going to shade that over here. Okay, so now we have the area under the curve of the required score, which is 152, to get in for admissions, shaded, okay, and to the right, which would be greater than. So anybody who makes a 152 or greater would be accepted into the school. Okay, now suppose the area under the normal curve above 152 is 0.4090. Provide an interpretation for this area. Well, this means that the probability of someone who took the GRE and being accepted into the school is 0.4090, okay? Or 40% or almost 41% of the people who take the GRE will pass the GRE sufficiently enough or score high enough to be accepted into the graduate school. Okay, standard units and areas under the standard normal distribution. We need to be able to find the areas of or probabilities, the areas or probabilities, one and the same, under the normal curve for values that do not fall at exactly the points that we have been discussing. In other words, the mean, plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations, or minus 1 standard deviation, minus 2 standard deviations, minus 3 standard deviations. We will use z-scores and a table to find those areas or probabilities. Just like we used the binomial distribution tables, we have the normal distribution table, okay? The normal distribution varies from one another's in two ways. The mean mu may be located anywhere on the x-axis, and the bell-shaped curve may be more or less spread according to the size of the standard deviation, okay? So some things may be clustered closer together or more dispersed away from the mean. The differences among the normal distribution cause difficulties when we try to compute the area under the curve in a specified interval of x values, and hence the probability that a measurement will fall into a particular interval. Because there are many centers and spreads for the normal distribution, for the most part infinitely many, we are interested in standardizing them. So if we can somehow or another standardize all the data, then we can compare all the data without any problems. If something has a mound-shaped distribution, we can standardize it to be what we call the standard normal, a normal distribution with the mean equal to 0 and the standard deviation equal to 1. We're going to use the table to help us find the probabilities of the normal distributions. The standardization allows us to use one table because it would be impossible to make a table for every single normal distribution out there. Okay, we use z-scores to standardize the normal distribution. Literally, if you think about babies when they're born, the doctors they measure certain parts of the baby every single visit. They take the length, they take the weight, they take the head circumference. And then they plot those measurements on a chart. And they say, your baby is in such and such a percentile, okay? Or compared to all the other babies in the U.S. that are born and are this age and this gender, your Sally Mae is taller, longer, shorter, lighter, heavier, whatever, or perfect. She's the perfect average baby, okay? So we standardize these values so that we can compare, make good comparisons. We may want to take and test a medicine between dogs and cats. Maybe we want to test the effectiveness of the medicine between dogs and cats. Well, dogs weigh more typically, okay, depending on the breed, than cats, right? They act differently. Their bodies process chemicals differently. And so we need to be able to somehow or another remove the variations of the differences in those different factors so that when we compare the effects of the medicine, we're comparing apples and apples and not apples and oranges. That's what standardizing the data does for us. That's what using the z-score does for us. We may have two different types of data, but they're both normally distributed. So now I can put them on a common scale and see how they truly compare against each other. Okay, so here we go. How do we standardize? How do we get data to be comparable and on the same scale? That's what we're going to be doing. We're going to be taking data from different scales, putting them on the same scale so that we can compare. Okay? Kind of think of it like this. Let's say you have a scale that weighs in kilograms and another scale that weighs in ounces. Wouldn't it be nice if we could convert both weights to pounds so that we could understand it? That's kind of what we're doing. We're going to be taking different distributions and converting them to a unique scale that is consistent so that we always understand what is happening because the scale is consistent and well defined. Okay. So, standardizing the normal random variable. Suppose that a random variable x is normally distributed with the mean mu and the standard deviation sigma. So, mu can be any number, sigma can be any number. Then we have the random variable z, which is going to be equal to x minus mu divided by the standard deviation. This is normally distributed with the mean equal to mu and the standard deviation equal to 1. The random variable z is said to have the standard normal distribution, okay? So it's said to have the standard normal distribution. After we convert our observations to z-scores, what does this mean? It means that a positive z indicates the original value is above or greater than the mean. The negative z indicates that the original value is below the mean, okay? Similarly, a value that is very close to 0 indicates that the original value is very close to the mean. A large z value indicates that the original value is far away from the mean. Okay? So let's look at this for just a minute. The standard normal curve, okay? We're having more power flickers, not good. Means that in the very center is 0. Our mean is equal to 0. One standard deviation away, let me switch colors there. One standard deviation away from the mean, I am not drawing straight lines at all, is +1 and -1 standard deviations. If we get a z-score of 2, it's +2 standard deviations, -2 standard deviations. If we get a z-score that is 3, that means I am 3 standard deviations above the mean. Or if I get a -3, that means I am 3 standard deviations below the mean. This is all symmetrical and evenly distributed bars. Just go with me on that. Remember, use your imagination when it comes to my artwork. Okay. Here's our formula for our z, okay, our z-score. Suppose a normal distribution has a mean of 53 and a standard deviation of 3.2. What is the z-score if x equals 50? So to find the z-score for x equals 50, it's going to be z is equal to 50, because that's what x is equal to. Subtract our mean. Mean is 53, subtract our mean, and divide through by our standard deviation, which is 3.2. It's really important, let me pull up my calculator here. It's really important that when you are doing these calculations that you know to use your parentheses and practice this prior to your exam, please. So many students still make mistakes on their exam because they did not practice the usage of their calculator prior to the exam. Or they borrow a TI-84 from a friend because they hear, oh, the TI-84 is going to be the miracle maker of me making a successful grade on my statistics exam, but they never used it before. Don't ever do that because you will not do well. You must be familiar with the calculator that you are using on the exam. Do not switch calculators prior to coming into the exam. Okay, so it's important that you put the numerator, that you put the numerator in parentheses, okay? Because we want 50 subtract 53 parentheses. Now my numerator is within parentheses. We're going to divide through by 3.2. And we get the answer is negative 0.9375. And that makes sense. It's a negative number, okay? It's a negative number, and 50 is less than 53. If we standardize 53, that's going to end up being 0 on our standardized scale. So since 50 is below 53, we would expect a negative number. So it's negative 9375. Negative 9375. That's our z-score. Now I want to show you real quick what happens if you don't use parentheses. This answer right here is the correct answer, okay? But what if I did 50 minus 53 divided by 3.2? Look at the answer, completely different. Instead of ending up with a negative 0.9375, I ended up with a positive 93.4375. The order of operation on the second one is completely different and wrong than the first one. So make sure you pay attention and you know how to use your calculator. In addition, if you ever got a z-score of a positive 33, something's probably very, 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 very wrong. Okay, so that would be something else that you would want to pay attention to. Now it says, what is the z-score if x is equal to 55? So we're going to calculate the z-score if x is equal to 55. So z is going to be equal to 55 minus 53 divided by 3.2. We're going to grab the calculator. We're going to clear it out. We're going to put parentheses, and we're going to go 55 minus 53, close parentheses, divide 3.2 equals 0.625. So this is going to be equal to 0.625. Now, let's look at what this really means, okay? Let's talk about our two different curves going on here. So we're going to draw our original curve for our original data. And our original data has a mean of 53. Then we're going to draw a curve right below it of the standard normal data. Okay? And the mean on the standard normal is always 0. If I wanted to look at one standard deviation above the mean, I would simply then take the mean, which is 53, and I would add to that the 3.2 because that's this one standard deviation, correct? And that would give me 56.2. So right here, let me switch colors. Right here is going to be 56.2. Now let's go one standard deviation below the mean. So 53 minus 3.2 is going to give me 49.8. So right here is 49.8. And yes, if I was drawing it, I would really want to go to the point of inflection on my curves, but I'm going to go off of the consistent width instead. Now if I wanted to go to 2 standard deviations away from my mean, I would say that 2 times 3.2 plus 53, that gives me 59.4. So right here is going to give me 59.4 right here, okay? It's 59.4. So if I want to go 2 standard deviations below the mean, that is going to give me 46.6. So 46.6. And if I wanted to take and go 3 standard deviations above the mean, it's going to be 3 times 3.2 plus 53. And it's going to give me 62.6. 62.6. And then 3 standard deviations below the mean. Again, it's going to be 3.2 times 3. That gives me 9.6. I'm going to subtract that off of 53, and I get 43.4. 43.4. Now, this is plus 1 standard deviation, minus 1 standard deviation, plus 2 standard deviations, minus 2 standard deviations, plus 3 standard deviations, minus 3 standard deviations from the mean, okay? Now, if I go ahead and I want to standardize each of these values, I've calculated what they are. This one should become the number 1, this should become the number 2, and this should become number 3. This should become negative 1, this should become negative 2, and this should become negative 3. Let's do the math and see if we can work that out and show you that, okay? So let's come up here with the first one, and let's standardize 1 standard deviation above the mean. So I'm going to say, what is z equal to? What is z equal to when x equals 56.2? So this would be 56.2 minus 53 divided by our standard deviation, 3.2. Grab our calculator, clear it out, put our parentheses. 56.2 minus 53 parentheses divided by 3.2. It equals 1. Right there, it equals 1. So right here is 1 standard deviation when x equals 56.2. Let's do 49.8. So z is equal to what when we have x is equal to 49.8? 49.8 minus 53 divided by 3.2. Throw that in our calculator. Okay, so let's do our math. So it's going to be parentheses 49.8 minus 53 parentheses divided by 3.2, and that's equal to negative 1. So there we go, negative 1. So let's go ahead, and that's negative 1. Whoops, that's crooked as a dog's hind leg. There we go, negative 1. Let's look at our 2 standard deviations. So what is z when x is equal to 59.4? Well, that would be 59.4 minus 53 divided by 3.2. Grab our calculator. Parentheses 59.4 minus 53 parentheses divided by 3.2, positive 2. What is z when x is equal to 46.6? So 46.6 minus 53 divided by 3.2. Throw that in our calculator. And we get 46.6 minus 53 parentheses divided by 3.2 parentheses negative 2. Oops. Let's standardize the value 62.6. So So we end up with z is equal to 62.6 minus 53 divided by 3.2. Throw it in your calculator. Parentheses 62.6 minus 53 parentheses divided by 3.2 is equal to positive 3. Oops, I didn't draw my 2 over there. Positive 3. Positive 2 from right over here. Now let's standardize 3 standard deviations below. Z is equal to 43.4. 43.4 minus 53 divided by 3.2. There we go. We're going to throw that in the calculator. And we get parentheses 43.4 minus 53 divided by 3.2. And that is equal to negative 3. So right here, negative 3. Negative 3. Okay, so I hope you threw some of these in your calculator. I hope you're practicing your math and calculator usage along with me as I'm going through and doing these problems. Very important that you can duplicate this on your own. So what did I just do? On the very first data set, let me grab a different color highlighter here. There we go, that's a little bit better. So on our original data set, we drew a distribution, a normal distribution with the mean of 53 right in the center. Then we calculated what was 1 standard deviation above the mean, 1 standard deviation below the mean, 2 standard deviations above the mean, 2 standard deviations below the mean, 3 standard deviations above the mean, 3 standard deviations below the mean. Okay, and I marked these on our curve. Now I can look at my x's. The first one says, what's the z-score of 50? So let's come in here and we're going to mark 50. Where's the point 50? It falls right about here, right? There's the point 50. And when we calculated the z-score, it came out to be negative 0.9375, almost negative 1 standard, negative 1, which would be negative 1 standard deviation. Do you see how close that is? So right here on our standard normal, this would be our z, our standard normal curve. When you see the word or hear the word standard normal, that's talking about the z. So this is going to be a negative 0.9375. So you can see these points are mirror images of each other. These graphs are set up identical. They look the same. The bottom scale is the only thing that's different, okay? And what I'm doing is I'm taking these values right here and I'm standardizing them and showing where they fall on the standard normal curve. Now let's look at the next z-score was 55. Well, where's 55 on here? 55 is right around in there, okay? When we calculated our z, it came out to be 0.625. So a little bit more than halfway through, 0.625. Do you see the correspondence here? So what we're doing is we're taking our data, it can be any data, and we're going to transfer it to our standard normal where it makes sense and it's on a uniform scale. And our scale says that 0 always represents the mean. That 1 always represents 1 standard deviation above the mean. Negative 1 always represents 1 standard deviation below the mean. Positive 2 always represents 2 standard deviations above the mean. Negative 3 always represents negative 2 always represents 2 standard deviations below the mean. Positive 3 always represents 3 standard deviations for any distribution, as long as it's normally distributed, above the mean. -3 always represents 3 standard deviations below the mean. Now the one calculation that I didn't do is this one right here. So let's go ahead and do that. What happens? Let's calculate the z-score for the mean, and let's show that that transfers to 0. My formula is x. Well, my x would be 53, if that's what I'm standardizing. So it'd be 53 minus the mean, 53. Oops. 53 divided by the standard deviation. I get 0 divided by 3.2, which is just 0. So that shows that when I take and standardize the mean, it will indeed equal 0. So all I'm doing is showing you that I can do this for any data set. As long as I put it on the standardized scale, if I use this formula, I'm putting it on a standardized scale. Now I can compare apples and apples. Okay? Because once I standardize it, it takes into account the standard deviation, how much variation is amongst your data. It removes that variation and puts it on a standardized scale so that we can do accurate comparisons. That's what we're doing. So what is the z-score for 50? That was the original question. A negative 0.9375, which I plotted right there. What is the z-score for 55? When I standardized it, it became 0.625, which I standardized right there. And that makes perfect sense. My x value is greater than my mean, therefore it's to the right. Here my x value is below my mean, and so it's going to be negative and to the left of my mean. Okay, let's practice some more. Okay, a pizza parlor franchise specifies that the average or mean, okay, average, mean, expected value, all meaning the same thing, amount of cheese on a large pizza should be 8 ounces and the standard deviation only 0.5 ounces. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it's mean with 6.9 ounces of cheese, okay? Assume that the amount of cheese on the pizza follows a normal distribution. If the amount of cheese is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchise. How many standard deviations from the mean is 6.9? Is the pizza parlor in danger of losing its franchise? Okay, so we're going to read it one more time, and I'm going to be highlighting. Let's highlight in this color right here. Okay, a pizza parlor franchise specifies that the average or mean amount of cheese on a large pizza should be 8 ounces, okay? So the average should be 8 ounces, and the standard deviation should only be 0.5 ounces. An inspector picks out a large pizza at random, and the random part is important, in one of the pizza parlors and finds that it is made with 6.9 ounces of cheese. Assume that the amount of cheese on the pizza follows a normal distribution. Very important. If the amount of cheese is below the mean by more than the amount of cheese, 3 standard deviations, the parlor will be in danger of losing its franchise. How many standard deviations from the mean is 6.9? That's the first question. And then, is the pizza parlor in danger of choosing its franchise? So what this means is I just simply need to standardize the value, okay? I need to calculate the z, because if I know the z, okay, think about it like this. We have a distribution, right? We have the mean at 0. It says if the amount of cheese is below the mean by more than 3 standard deviations, so below 3, so if it's in here, I'm in danger of losing my franchise. As long as my z-score is above a -3, I'm good. I don't have to worry about losing my franchise, okay? So let's go ahead and standardize. So z is equal to x minus mu divided by sigma. So what is my x? My x is going to be 6.9 ounces. That's what my random pizza, that's how much cheese my random pizza had on it. So it's 6.9 minus, what would it, should it have? 8. And it should only have a standard deviation of 0.5. Okay, so now you're going to grab your calculator, and I'm not going to do the calculator because I've already demonstrated how to use your calculator. So grab your calculator out and calculate it yourself. I'm working mine very slowly to give you a chance to catch up. Pause your video if need be. And did you get negative 2.2? I hope that you did. So right over here is where the negative 2.2 is on our standardized scale. So how many standard deviations from the mean is 6.9? It is 2.2 standard deviations from the mean, okay? Once I standardized it, I find that the value 6.9 is 2.2 standard deviations below the mean. Am I in danger of losing a franchise? No, because my standard deviation was not below negative 3. I was not more than 3 standard deviations below the mean or the expected value. Okay, let's work another example real quick. It says Rod figures that it takes on average being mean, of 17 minutes with a standard deviation of 3 minutes to drive from home, park the car, and walk to an early morning class. On one day, it took Rod 21 minutes to get to class. How many standard deviations from the average is that? So let's just look at part A. Okay, again, let's do some highlighting. So Rod figures that it takes an average of 17 minutes with a standard deviation of 3 minutes to drive from home, park the car, and walk to class for early morning class. On a particular day, it took Rod 21 minutes to get to class. How many standard deviations from the average is that? So part A. We're saying we need to calculate the z-score because the z tells us how many standard deviations a data value is from the mean. We just need to standardize it. Remember, z is equal to x minus mu divided by sigma. So my x is going to be the actual observation of how long it took Rod to get to school, which was 21 minutes. Minus my mean, and my mean is 17 minutes, divided by standard deviation, which is 3 minutes. Okay, pause the video, grab your calculator, punch it in, and what did you get? I got 1.33. When it comes to the z-score, you only need to go to 2 decimal places, round off accordingly, okay? Using normal rounding parameters. Okay, so what is the standard deviation? 1.33. Part B. It says, what commuting time corresponds to the standard deviation of 2.5? Or negative 2.5. There's a negative there. So it says what commuting time corresponds. So I'm solving for x in that case. I'm given a z. I know my mean. I know my standard deviation. I'm given my z. I know my mean. I know my standard deviation. I'm being asked for x. So let's plug in what we know. We were given that z is equal to negative 2.5. So negative 2.5 is equal to x minus our mean, which is 17, divided by our standard deviation, which is 3. This is a simple algebra problem. Just solve it like you would any other algebra problem. You're solving for x. We even have it set up for x, okay? So in order to do that, we're going to multiply both sides through by 3. So I end up with 3 times negative 2.5 is equal to x minus 17. I can add 17 to both sides. And I'm going to get 3 times negative 2.5. Until my computer's getting hot, it's not keeping my small marks, plus 7. And that's going to equal x. And I'm writing it like that instead of solving it for a particular reason. You'll see that in just a moment. Go ahead and grab your calculator, solve it. So 3 times negative 2.5 plus 7 is negative, or 17, not 7, plus 17. Let's try that again. So it should be 3 times negative 2.5 plus 17, and that is equal to 9.5. So therefore, oh, my computer, x is equal to 9.5. Okay? I left it in this form because I want you to realize that I can rewrite the whole formula as x equals, what is this? Okay, this is our standard deviation, or I'm sorry, yeah, our standard deviation multiplied by our z. So it's going to be z times our standard deviation, or standard deviation multiplied by z, order is not important with multiplication, plus what was my 17 right here? My 17 is mu. And that's what x equals. So you can actually write this down and hang on to that formula just like you hang on to this one. It's helpful. I don't necessarily recommend memorizing the second formula because all you ever have to do is set it up as an algebraic equation and solve, just like we did right here. So it says, what commuting time corresponds to a standard score of negative 2.5? The commuting time would be 9.5 minutes. Okay, I promised you that there would be tables that you can use for the standard normal, just like we had the binomial tables. Okay, those are already posted in e-learning for you, and they are set up. We have two different tables for the standard normal, and they are set up in this manner, where the first page is that you're always given the probability of the area under the curve to the left of your z value. Okay, so the table, and it occurs in the e-learning, corresponds to the probability that everything to the left of z. So to find the probabilities, we can use the fact that the total probability under the curve is 1. Okay, so we can take advantage of that plus advantage of the symmetry. Okay, so we know that this whole area is equal to 1. So if I needed to find something in here, I can take and subtract this part off of the number 1, and I would find the difference here. Okay, we're going to do several examples. Okay, here we go. In the IQ example that we discussed earlier, IQ scores can be modeled with a normal distribution with a mean of 100 and a standard deviation of 15. In individuals whose IQ score is 120 is 1.33 standard deviations above the mean. So that means when we take and calculate the z-score, we put in 120, okay, for the individual, minus the mean, divide it through by the standard deviation, and that equals of 1.33. So we have a z-score of 1.33, or we are 1.33 standard deviations above the mean. How do we know this? We can convert it to the z-score. Okay, the area under the standard normal curve to the left of 1.33 is 0.90824. You can find this by using the table and the standard normal distribution values. Okay, so here's how this works. Okay, I went and grabbed the UWF table, the one that was I was using for inserting into the notes from other notes, was not the UWF one, so I want to make sure I use the same table as that you're going to be using. So you're going to see that our table is only to 4 decimal places, not 5. So here's a picture. We have 2 tables with UWF. Let me just go ahead and switch screens to show you this real quick. We actually have 2 tables with that you will have. You're going to have with the negative z values, and so always look at your key. So you're always given to the area to the left, okay, on the UWF tables. And so if you have a negative z, you're going to look it up on this part in here, and it's always going to give you the area to the left of the tables. If you're given a positive z, again, it's going to give you the cumulative to the left. So it's going to be the area all the way over to negative infinity. So the green shaded area is what you're going to see. So when we look at our table, let me switch back to our other over here. When we switch over here, we need to look up the value of 1.33, and it says the area under the standard normal curve to the left, okay, is what we're looking for. So here's our z, and we're going to go to 1.3, but remember it's actually 1.33. So this column here gives you your decimal place to the tenths. To get to the hundredths, you go up here. So to get to 1.33, you combine these two columns. So you get the 1.33 right there, okay? And now you look at the intersection of this column with this row, and here is your area under the curve to the left of your z value, okay? So it's the area to the left of the z value is equal to 0.9082. 0.0982, okay? So this one here is 0.09824, gave a little bit more detail than this one right here. So to summarize an actual practical interpretation, so the fact that we end up with this 0.9824 or 982 in our case for the UWF tables, this means that the probability of selecting an individual whose IQ score is less than 120, because that's what we were standardizing was 120, is 0.90824 or 9082, and the proportion of individuals who IQ scores is less than 120 is 0.0982. Okay, so that's what the proper interpretation is. So here's your basic instructions of how to use a left-held standard normal table, which is what you're given. For the areas to the left of the specified value of z, you just use the table directly. It's going to give you the area to the left. For the areas to the right of the specified z, you look up the table entry for z and then subtract it from 1, okay? Because remember, the area under the curve for the entire curve is equal to 1. For the areas between two values, z1 and z2, where z2 is greater than z1, subtract the table areas for z1 from z2. We're going to go over several of those examples, so just hang tight. Okay, here we go. It says, find the area under the standard normal curve to the left of z is equal to -1. So the key part here is, let me grab a highlighter, is that we want it to be to the left of -1. So let's find -1 on our table here. So here's our z table right here, and we're going to come down till we find -1.0. -1.0 is right here, and we don't need anything in the hundredths, so it's going to be this right up here, and we're going to look at the intersection of the 2 points, and so the area to the left of -1.0 is 0.1587. So it is 0.1587. So the probability that z is less than -1.00 is equal to, my memory's short, maybe you wrote it down, I didn't, let me go grab it again, 1587. 0.1587. Okay, so now it says find the area to the left of z equals to +1.18. So to write that down properly, it looks like this. It's the probability that z is less than 1.18. Okay, so z is less than 1.18 because we're looking for the area to the left. So z is less than. So let's go find 1.18, and let's grab a pink highlighter. Since we're writing in pink, we're going to go to the positive, and we're going to find 1.1. So there's 1.18. There's the hundredths right up there, okay? And we're going to look at the intersection of this row with this column, and we end up right there. So it's 0.8810. So that is equal to 0.8810. So again, because it's said to the left. Okay, here we go with another example. It says, find the area between z equals 100 and z equals 270. So we're looking for the probability that 1.00 will be less than z, which will be less than 2.70. I need to cover something here because we're talking about continuous data. We can write this as strictly less than. We could write it as this side strictly less than or equal to, and this strictly less than. We could write it as this side strictly less than, and this side strictly less than or equal to, or we could put an equal sign on both, okay? It does not matter. All of those with the continuous data set are the exact same, okay? So it doesn't matter. You can put them on, you can leave them off, okay? So this is going to be equal to, let's draw a picture. Pictures in my class are worth a lot of points. So draw a picture of what we're looking for here. We have a picture. We have mean in the center. We have a value here of 1.0. We have another value of 2.70. We are looking for this area in here. That's the area that we're looking for. I want you to notice though that our tables give us this area, right? Okay, so if I look up 1.0, it's going to give me this whole area to the left. If I look up 2.7, I'm going to get this whole area in here, correct? But all I want is the blue. So if I look up the area under the curve at 2.7, which is this whole area in here, and then I subtract off the green shaded area, what am I left with? I'm left with the blue shaded area. So what we're going to do is we're going to look at the probability that z is less than 2.70. We're going to subtract off the probability that z is equal to 1.0, and that difference is going to be the blue shaded area, which is what I want. So here we go. So this is going to be equal to the area under the curve from negative infinity to 2.7. That's going to be this pink area. Okay, so let's come on down here and find 2.70. So we'll grab pink, 2.7, and 0 is going to be our first column. So let me scroll on up. So there's my first column right there. And we look at the intersection, so this is going to be 0.9965. 0.9965. So it's going to be 0.9965 minus the area, the green area here, where z is less than 1.0. Okay, and let's find that. So 1.0, again, my hundredths is 0, so I'm going to look 1.0, it's going to be this area, in this area, the intersection, which is 0.8413. 0.8413. Pause the video if you need to, okay? And we're going to come up here and make it 0.8413. Grab your calculator out and do your math, and 0.9965 minus 0.8413 is equal to, oops, I hit something wrong. Let's try that again. 0.9965 minus 0.8413 is equal to 0.1552. And that should be the area in the blue. Right in here should be 0.1. Oops, is it going to write? Oh, I don't have the right color. 0.1552 is the area under the curve between those 2 points. Let's look at another question right here. Find the area to the right of 0.94. Okay, so find the area to the right of 0.94. We'll go to purple for that. Right there. So to the right of 0.94. Let's draw a picture of what we're looking for. Okay, so we're going to draw a picture. It's going to be representing what we're looking for. Put our mean. Our standard deviation, or the z-value rather, is 0.94. And we are looking for the area to the right. Okay, so that's what we're looking for, the area to the right of 0.94. What do my tables give me? My tables give me all of this over here, correct? That's what my tables give me. So let's look up the area in the tables in purple, subtract it from 1, because I know this whole area is equal to 1. And so if I subtract off the purple from 1, what am I left with? The part in blue. So let's go ahead and write that down. This is going to be the same thing as the probability that z is greater than, because to the right, 0.94. And so this is going to be equal to 1 minus this probability right here, which is 0.94. Let's go find that. 0.9 right here. And then my hundredths is right there. Looking at the intersection of the two, it's 0.8264. 0.8264. .8264. I hope my memory held out well for me there. And we're going to go 1 minus 0.8264, and we get the difference is 0.1736. So this area in here is the 0.8264, and this area in here is the 0.1736. Okay, so that's a picture that represents what we're looking for. Let's do another problem. Okay, so here you go. If you feel like you've got the concept pretty well underhand, go ahead and find your tables that are in e-learning and solve these two problems. If you just pause the video, solve them, and then push play to see if you got them correct. If you're still not feeling very confident, just hang in there right now and I'll go ahead and solve these two. So if you're feeling confident, go ahead and pause the video, solve them, and then push play. If you're not, let's go ahead and work this one together. So again, this says find the probability that z is greater than or equal to 1.5. You see the equal sign right there? Again, remember, that does not make any difference, okay? It does not have any bearing on this. So let's go ahead and draw a picture first for part A, and we have our picture looking like this. In the very center, we're going to put our mean of 0. The area of interest is 1.15. 1.15. It says that z has to be greater than 1.15. So to be greater than 1.15, it's going to be this area over here. Okay? Ah, thank you. Okay. So the area that we're interested in knowing is actually this orange shaded area. Our tables give us this area over here. So I need to look up this area, determine how much is the purple, subtract it from 1, and then I'll have the orange area, the area of interest, left. So we have 1.15. We don't look at this area because this is negative. We're going to come in here and look for the number 1.1, and then 5 is right here. We're going to look at the intersection of the two, and it's right there at 0.8749. 0.8749. So this is 0.8749. Okay, and then this area right here will equal 1 minus 0.8749. Turn on our calculators. 1 minus 0.8749, and that is equal to 0.1251. So the area under the curve to the right of z equals 1.15 is equal to 0.1251. Let's draw a picture for our next question. So we draw our standard normal curve. We put our 0 in the center because that is our mean. And it says, I want to know the probability that z will be less or greater than negative 1.78, but yet less than 0.35. So it's a negative and a positive. We have negative, whoops, let me switch colors here. Negative 1.78, and then a positive 0.35. Let's see here, is it this one? What color is that? That's purple. This is green. That's pink. I'm looking for yellow. So let me come in here and grab yellow right there. Okay. So, we are looking for the area between the two. So this part here gives me, the tables give me this part right in here if I look up 1.78, correct? If I look up 0.35, I'm going to end up with this under the z tables. The area of interest is the area in blue only. So then I will have to subtract off this yellow part right in here from this blue part, okay, from this whole blue part, and then all I have left is the sky blue, okay? So if I deduct what I originally highlighted as yellow from this whole blue area, okay, so basically if I deduct the green spot that overlaps, I end up with what I'm interested, which is left, which is what's left. So the greater of the two numbers is going to be the 0.35. So I'm going to start with that to begin with. And I'm going to say that this is equal to, in this case, it's equal to the first number, which is 0.35. Let's go look that up. 0.35, 0.3, and then 5 right here. So it's 0.6368. .6368 minus, now that was from negative infinity to 0.35. Now we're going to subtract off from negative infinity to negative 7 or 1.78. So 1.78 negative. So negative 1.7, and then 8. Looking at the intersection of the two, it's right there. 0.0375. 0.0375. 0.0375. Throw this in our calculator and we get 0.6368 minus 0.0375, and we find the area under the curve is there we go, come on, 5993. 0.5993, and that's the area under the curve in the sky blue region. Okay, so the area from negative 1.78, which is less than z, which is less than 0.35, is equal to 0.5993. Okay, so this area in here in the blue is 0.5993. Okay, so that's how we're working with the tables. Okay, we're starting another little section. We're just going to build on what we've already know. Areas under the normal curve. In the last section, we discussed the standard normal. Recall that the normal distribution with mean equals 0 and standard deviation equals 1. Now we're going to use this to discuss any other normal distribution. Again, we're talking about a standard normal. We are taking any normal distribution and we're standardizing it. The formula that we're going to use is z is equal to x minus mu divided by the standard deviation to normalize the data that we've been given. Okay, here we go with another problem. So suppose x has a normal distribution, again that's important, with mu equal to 10 and sigma equal to 2. Find the probability that an x value selected at random from the distribution is between 11 and 14. So we could write that as the probability that 11 is less than or equal to x, which is less than or equal to 14. Let's draw a picture of what this looks like. So we have the probability that that 11 is less than or equal to x, okay, between equal to, doesn't matter, x is less than or equal to 14. Our picture is going to look like this. Oops. Let's see here. What is our mean? Our mean is equal to 10. And we're looking for 11 to 14. Both of those values are greater than 10. Oops, I know I switched colors. Okay, now I have my colors straightened out there. And we're looking for the area in between these two values. Okay, so we're looking for this area right in here. What's the probability that I randomly select an x and the x, the data point or the data that I observe, is between 11 and 14? So this picture represents what the question is, and in order to solve this I need to standardize each value, the 11 and the 14. So we're going to go ahead and rewrite this, and we're going to say this is the same thing as the probability of z is some value is less than z, which is less than some other value. What those values are, I don't know yet. I need to standardize each of these values, and then I will know. So if I first want to standardize 11, I'm going to say z is equal to 11 minus the mean. The mean is 10, divided by my standard deviation, which is 2. And I punch that in my calculator. I'm going to end up with 1 divided by 2, which is going to be 0.5. So my first boundary is going to be 0.5 is less than or equal to z, which is less than or equal to, now I want to standardize my 14. So z is equal to 14 minus 10 divided by 2. 14 minus 10 is 4. 4 divided by 2 is 2. So put my 2 right there. So these two expressions are the exact same. Okay? These two expressions are the exact same. So what is this equal to? Well, let's draw our standard normal right below it. You notice I always do one right above the other. I think that's important so that we can see exactly what's going on and kind of compare everything a little bit easier. So this is going to be 0.5. This one right here is going to be 2.0, and we're going to highlight. This is the area that we're looking for. Okay, so now I've taken my raw data, I've standardized it. Now I can use my tables to solve this problem. Okay, so here we go. First thing we need to do is find out the value or the area under the curve to the left of z, because that's how our table works. So let's highlight that. we're going to put that in a light yellow, a light green. So this area right here, that z is less than 0.5, is going to be this part right here. Okay, so let's look up the area under the curve that is in the green spot right here. Okay, so we're going to look up a z value of 0.5, positive. So we're scrolling on down to 0.50, so it's going to be this value right here, 0.6915. 0.6915. So we know that the probability that z is less than 0.5 is equal to 0.6915. I'm going to double check my memory on that. Hope my scrolling isn't bothering anybody. Sorry about that if it is. Okay, now the next area that we need to be aware of is what is the probability that z is less than 2. Okay, because there's our 2 right there. So we're going to come in here, and the probability that z is less than 2, let's make that brown right there. So the probability that z is less than 2 is all of this through here. Okay, it's all of that. So let's go down and look for 0.2. And so we're on our positive. We look for 2.0, 2.0, and it's 0.9772. 0.9772. So this is 0.9772. Okay, so the brown area is 0.9772. Let me circle that in brown actually. So the brown area is 0.9772. The lighter green area is right there. And the difference should give me the purple, right? So let's come up here and we will say that the probability that 0.5 is less than z, which is less than 0.2, is going to be equal to 0.99772. Subtract 0.6915. And the difference of those two numbers, punch them in my calculator, is 0.9772 minus 0.6915, and that is equal to 2857. So that's 0.2857, and that is in the ever so wonderful purple color right there. Okay, so 0.2857, 0.2857. Now, scrolling right on up. These are mirror images of each other. This is the standardized distribution representing this data right here. So we know then that the area under the curve right here is 2857, just like this area right here. So we know that this is equal to 0.2857. Okay? Okay, this is going to be a review. I want you to pause the video. I want you to solve this problem. And then when you've got the answer, I want you to push play. Once you see if you got the answer correct, you can go ahead and fast forward right on through the explanation. If you don't feel like you can do it, then follow along. Okay, I'm assuming that if you're here right now, you wanted to see the explanation. So it says, find the area under the standard normal curve in between z equals 1.425 and z equals 2.56. Let's write that down as a probability. This is the probability that 1.42 is less than z, which is less than 2.56. Okay, that's mathematically written down. Now let's draw a picture to represent this. Again, we've already solved all these, so this is a little bit of a review. If you're still struggling though, hang on. Okay, we draw a standard normal. We're now going to put our lower bound in first. It's a positive 1.42, which tells me I go to the right of my mean, and it's going to be 1.42. Now my other boundary is positive 2.56. Now, why am I writing them this far apart? I'll tell you why. So that you can see legibly what I'm writing down here, okay? Obviously the 1.42 would be more over here, okay? But because I want you to be able to read my writing, I'm spreading them apart more. Okay, so we've drawn a picture of what we're looking for, and we're going to highlight the area of interest. We're looking for this area between these 2 points. As it says, find the area under the standard normal curve between those 2 points. So that's how we know what we're looking for. Well, our tables give us from negative infinity to the value. So the first value I'm going to look up is the probability that z is less than 1.42. That is going to give me this area right in here, okay? That is going to give me this area right in here. So let's go find that, 1.42. I need to come to our positive tables. To z is 1.4. Now we got to come to the 2. Look at the intersection of those two, and that's 0.9222. So this is equal to 0.9222. Now the next one I need to look up is this one right here. Let's pick a color for that one. Let's see here. Let's do purples. So we're going to say this is going to be equal to the probability that z is less than 2.56. Okay, so now we're going to highlight gently the area in purple that represents the area under the curve that is less than 2.52. Okay, so less than 2.52. Again, positive 2.5. So here's our z coming in, looking for 2.5. It's right there. We'll scroll a little bit more. 2.5. Now let's find the 0.6. Here's the 0.6 right here, okay? So now we have to come down this column right here until it intersects with the 2.5. Was it this one? Let's see here. Oh, I don't remember if that was it or not. Let's see here. Yes, that is. So it's 0.9948. 0.9948. So 0.9948. So the area in the blue here is 0.92, oops, 9222. The area in the purple is 0.9948. And what I need to know is what is the area in the pink, okay? To calculate the area in the pink, I'm going to take the area in the purple, which is 0.9948, and I'm going to subtract the area in the blue, which is 0.99 or 9222. And that difference, if I take this whole purple and I deduct this blue, what do I have left? The pink. So we're going to grab our calculator, and I'm going to go 0.9948, subtract 0.9222, and I end up with 0.0726 right there. Okay, so this area in here is 0.0726. So what we're really saying is 0.92222 plus 0.0726, adding those two together, that equals the 0.9948, okay? Because we have the blue, we have the pink, we add them together, and we get the 0.9948. What am I interested in my area, though? This area right in here. So the area under the curve between 1.42 and z equals 2.56 is 0.0726. That's my answer. Okay, here's another one. Go ahead and push pause. See if you can solve this on your own. If you can't, then just go ahead and watch the video. But if you think you've got it going on, you've got a good handle on this concept, pause the video, give it a shot. Worst thing that happens is you make a small mistake and then you watch the video and you figure it out. It's a really good idea for you to go ahead and just try this one on your own. Don't forget, draw a picture. Always, always, always draw a picture. Okay. I'm assuming if you're still here, you are ready to have me solve this problem. So here we go. First thing I'm going to do is draw my picture of the question. This says, find the probability that negative 1.32 is less than z, which is less than 1.34. So here's my picture in the center, because it's a standard normal. I know it's a standard normal because I'm dealing with z's and not x's. So my mean is 0. I'm going to go ahead and grab my other ink, and I'm going to switch to pink. I'm going to put my negative 1.32, and then I'm going to put my positive 1.34, and I'm going to highlight the area of interest. My area of interest, oops, I really want it pink. It's hard for me to tell which one is pink at times. Maybe it's this one here. Here we go. So, the area of interest between the two numbers is this right here. I'm looking for the probability that I end up with a z value between negative 1.32 and positive 1.34. So let's calculate first. We're going to calculate this area right in here, which is the probability that z is less than negative 1.32. So what area am I shading? I'm shading this area in here because this is what your tables give you. So when we look up in the tables, this is what I'm given. So when I look up negative 1.32, my tables give me this area in here. And let's go look that up. So negative 1.32. Oops, I did not print out my tables. So let me print out my tables real quick. Hang tight. Okay, here we go. We're looking for the area under the curve to the left of negative 1.32, or that z is less than negative 1.32. So we're going to be in the negative. Here's my z. We're looking for negative 1.3 and then 2. And now we're going to look at the intersection of those two. The row in the column is 0.0934. 0.0934. 0.0934. Boy, we're getting a lot of electricity flickers. I hope I don't run out of electricity before I finish this lesson. There we go. So that is the area under the curve is 0.0934. I need to know this area in here. So now if I look up the area for 1.34, that would give me this whole area. And then if I deduct this, what do I have left? The area in the pink. So let's choose another color for over here. We'll use brown. I think sometimes that contrasts okay. Yeah, it's about the best I can do on contrasting. So now we're going to look up this probability right here, the probability that z is less than positive 1.34, and that will give me this whole area, okay, that I kind of highlighted there in the brown. So positive 1.34. Grab my ink, and here we go. So we're going to go to the positive z tables. And here's my z, 1.3 and 4. And we're going to look at the intersection, and it's right there at 0.9099. So So 0.9099. So my whole area in my brown here, I'm going to write it in the brown spot, is 0.9099. That's in the brown. And what I need is the pink. So my pink is going to be equal to the probability that negative 1.32 is less than z, which is less than 1.34, is going to be equal to the brown area, which is 0.9099, subtract off the blue area, 0.0934, and the area that I have left is the area in the pink, and that is equal to 0.9099 minus 0.0934, and that is equal to 0.8165. So this area in the pink is 0.8165. And this is the answer that we're looking for. How'd you do? If you got this correct and you did it as a your turn, I want you to send me an email or a text that says, well, I was going to say hurricane party, but let's not do that. Let's see here. Let's just say stormy. So if you got this correct, and before I solved it, I want you to email me or text me the word stormy. Then I'll know that somebody, at least one person maybe, got this correct as a your turn. Let's move on to the next problem. Okay, here we go.